Welcome to this lecture on game theory. In this session, we will explore how game theory provides a framework for understanding strategic behavior, how people, firms, and governments make decisions when their outcomes depends on what others do. Game theory models situations where players, such as individuals, firms, and political parties, make strategic decisions in response to others' actions. For example, firms competing in an oligopoly decide on prices while anticipating rivals' reactions. Or political parties choose positions on issues before elections, considering where other parties stand. Even nuclear deterrence, like the scenario depicted in the 1983 movie War Games, relies on strategic interdependence. The goal of game theory is simple but powerful: to predict and design behavior in strategic settings. Game theory is widely used in public policy and economics. In tax competition, jurisdictions strategically choose tax rates while responding to the actions of their neighbors. In climate negotiations, each country decides its emission level with anticipating how others might respond. As mentioned before, oligopolistic firms strategically set prices or quantities, knowing their decisions affect the entire market. And in public goods provision, individuals must decide how much to contribute when benefits depend on everyone's participation. A familiar everyday example is the self-fulfilling prophecy we see during crisis. When consumers feel shortages, say of toilet paper, they start buying more. If everyone did that, shelves would empty quickly, creating the very shortage they feared. Each person's decision depends on expectations about others, and that interdependence is exactly what game theory captures. Now, let us have a look at the game components. Every game has three core components: players, actions, and payoffs. Players are the decision makers. These could be firms, individuals, or governments. Each player has a set of possible actions, such as whether a firm keeps prices high or cuts them. Payoffs represent the outcome each player receives based on the combination of everyone's actions. These payoffs could take the form of profits, utility, or satisfaction. Game theory assumes that the payoffs can be ranked, allowing us to analyze rational choices. Now, let us have a look at types of games. First, we are going to look at cooperative versus non-cooperative games. In cooperative games, players can form binding agreements to coordinate actions and share payoffs. In non-cooperative games, which are the focus of most of game theory, players act independently. Their welfare depends on both their own choices and the choices of others. Even when cooperation occurs, it is often the result of rational, self-interested decisions rather than explicit agreements. In a game of complete information, all players know the structure of the game, the set of players, the available strategies, and the payoffs. They also know the order of play and what information each player has. Classic examples are Prisoner's Dilemma, Cournot and Bertrand competition, and entry deterrence when costs are known. When all this is common knowledge, uncertainty arises only from the strategy, not from missing information. In contrast, incomplete information exists when at least one player holds private information unknown to others. That could be a private cost, a hidden constraint, or an observable type, say whether a firm has high costs or low costs. The other players must form beliefs about this hidden information, often using probabilities and expectations. Much of modern game theory builds on this idea of strategic uncertainty. A key concept of game theory is the Nash equilibrium, which can be considered the central concept in non-cooperative game theory. A Nash equilibrium is a stable outcome where no player can improve their situation by changing their own action, given what everyone else is doing. Each player's strategy is a best response to the strategies of others. It doesn't necessarily represent cooperation, it represents mutual consistency. To identify a Nash equilibrium, we list all strategies, find each player's best response, and locate the point where those responses intersect. Note that a Nash equilibrium is what players will do and not about what players should do. Economic models based on game theory are simplifications of real strategic interactions. They help us formalize incentives, competition, and cooperation in a way that allows prediction and policy analysis. Game theory extends standard economic models by explicitly including strategic interdependence, how each agent's payoff depends on others' actions. It provides a systematic framework for analyzing negotiations, conflict, and coordination across markets and policies. A player's strategy is a complete plan of action for every possible situation in the game. If someone else followed your written plan, they could replicate your choices exactly. A game may have one unique equilibrium or multiple equilibria depending on how strategies interact. Some games have no equilibrium in what are called pure strategies, but require players to randomize. This leads to mixed strategies. And later on in this video, we are going to look at some of those examples. Now, the most famous game is the so-called prisoner's dilemma. So here's the situation. Two suspects are arrested for a joint crime and interrogated separately. Prosecutors lack enough evidence for a major conviction without a confession, but they can convict both of them on a smaller charge. Each prisoner faces the same deal. If one confesses and the other stays silent, the confessor goes free and the other gets a heavy sentence. If both confess, they each get a moderate sentence, and if they both remain silent, they receive only a light sentence. Now, this situation is depicted here in this prisoner's dilemma payoff. Note that we have the two players, A and B, and if they both do not confess or do not cooperate with the police, they both get 1 year of prison. If they both confess, they get a lighter sentence of 5 years each, and if only one of them confesses, the person confessing goes free. That is depicted, for example, if player B confesses, player B gets 0 years in prison, and if player A denies in that case or does not cooperate, player A would get 20 years in prison. So here, prisoners must decide without knowing what the other one does. When we are solving this game, that the outcome is that both are confessing, despite the fact that this is not the optimal outcome in this game. Now, let us have a look at the prisoner's dilemma here. So, as you can see, we have player A that can play deny, and then the payoff for player A would be the 1 if the other player denies as well. For player B, we have the second spot here, okay, or the second after the comma is the payoff for player B. Now let us go through this game and see what the Nash equilibrium are. In order to find any Nash equilibrium, we are first going to fix the action of one player. So assume that player B is playing deny. Then player A has the choice to play either deny or confess, and clearly confessing here is the better option because it only gives a prison sentence of 0 years compared to 1 year. Now, if player B confesses, then player A has to choose between deny and confess. And here again, confessing is the better choice because 5 years of prison are better than 20 years of prison. Now we are reversing the roles and see, okay, if player A denies or does not cooperate with the police, then what is the best choice for player B or the best action for player B? Well, the best action for player B is in this case to confess, since 0 years are better than 1 year. And if player A confesses, then the best choice for player B is also to confess. And hence we have the Nash equilibrium here, which is indicated as both players confessing. Okay, since we have both outcomes underlined in this payoff matrix. Now the question is, why is the optimal option, or if you think about the optimal option for both players, would be to actually deny and not cooperate with the police, because 1 year of prison for each is better than 5 years of prison for each. Okay. Now the problem is that the deny is not a Nash equilibrium, since individual players have the incentive to deviate. To see how this works is, imagine that we are starting in a position where both players are actually denying, so they both get 1 year of prison. But then player A has the incentive to exchange that year for prison from 1 year to 0 years if the player A confesses. The same is true for player B, who can now convert a prison sentence of 1 year to a prison sentence of 0 years. Okay, so here the 1-1 is not an equilibrium, because they each have the incentive to deviate from that action. Now suppose that they are both in the situation, and note that here the outcome is symmetrical, where they are in this situation of 20 years. So one confesses and the other one denies. So then player A in this situation would get 20 years and player B would go free. Now in this situation too, player A has the incentive to actually deviate to exchange 20 years of prison for 5 years of prison. And hence, again, this asymmetric information, or this asymmetric outcome where one denies or does not cooperate with the police and the other one confesses, is not a Nash equilibrium. Okay, so the only Nash equilibrium here in this game, okay, is where the both players, or both prisoners are confessing, and we have the outcome of 5 years and 5 years for each of them. Now let us have a look at another game, the so-called cartel game. Cartels work much like repeated prisoner dilemmas. Firms collude to keep prices high, but each firm has an incentive to secretly cheat and capture an extra share of the market. This makes collusion fragile and dependent on trust and monitoring. Antitrust policies exploit this instability, particularly through leniency programs that encourage defection. These programs turn long-term cooperation into a one-shot prisoner's dilemma, leading to the collapse of the cartel. In order to illustrate the cartel game, let us consider the following payoff matrix. We have two firms, and if they do not cheat in the sense that they are forming the cartel, their payoff is 50. However, if one of them cheats in the sense that they lower prices in order to get a larger share of the market, their payoff is going to increase to 54 at the expense of the other firm's market. Now let us see what the Nash equilibrium is in this situation. Now let us look at how to solve this cartel game. And here we have again two firms, A and B, and they each have two actions, cheat and don't cheat. So as before, we have firm A, and the payoff of firm A is always marked before the comma. And we have firm B, and the payoff of firm B is marked after the comma. Now let us consider the actions of firm A. And as before, we are fixing the actions of firm B. So here in this case, we start with that firm B does not cheat. And then the question is, if firm B does not cheat, what is firm A going to do? Well, in this case, firm A is going to cheat because 54 is better than 50. And if firm B cheats, then here firm A is going to do again cheat as well, because 48 is better than 45. Now let us turn to fixing the action of firm A. So here, if firm A does not cheat, then firm B should be cheating, because 54 is better than 50. And if firm A cheats, then firm B should cheat as well. And hence we have here the Nash equilibrium, okay, which is playing 48 and 48, or put differently, to cheat and cheat. Now, as before, you can see that theoretically it would be better for both firms if they played do not cheat, but this is not a Nash equilibrium. And so here is why. So consider that both firms are initially in, are agreeing to not cheat and price, for example, high, and they both get 50. But this is not an equilibrium, because firm A has the incentive to deviate from 50 to cheating, because 54 is better than 50. And the same is true for firm B, that would deviate from 50 or from don't cheat to cheat, because the payoff is higher than, the payoff from cheating is higher than the payoff from not cheating. And once we are in the situation where one firm cheats and the other one does not cheat, then, for example, for firm A, it would be better, in the situation where firm B cheats, it would be better to switch to the cheating as well. So here, the only Nash equilibrium is the situation where both firms are cheating. Now, the next game that we are going to look at is the well-known rock, paper, scissors. Some games, like the one we just mentioned, have no Nash equilibrium in post strategies. Each action can be beaten by another. Rock loses to paper, paper loses to scissors, and scissors lose to rock. The only equilibrium occurs when each player randomizes equally across options, making behavior unpredictable. We will soon see that this is called a mixed strategy. But let us first show that rock, paper, scissors does not have a pure strategy Nash equilibrium. Now let us look at the situation where we have two players and they're playing rock, paper, scissors. And here we are going to look at a situation where there is actually no Nash equilibrium. Now, as before, despite the fact that we now have a slightly larger game matrix or payoff matrix, the strategy to find the Nash equilibrium that doesn't exist in this case is the same. So here, let us see why. So consider player 2, and let's assume that player 2 is playing rock. Then, in that case, player 1 should be playing paper in order to win. Okay, so here for red is player 1. If player 2 plays paper, then player 1 should play scissors. And if player 2 plays scissors, then player 1 should be playing rock in order to win. Now let us switch the roles and let's look at player 2 that I mark in blue here. So now if player 1 plays rock, then player 2 should be playing paper to win. If player 1 plays paper, then player 2 should be playing scissors to win. And if player 1 plays scissors, then player 2 should be playing rock to win. So note that here you do not have a situation where a single cell has two markings, and hence here we have a situation where we have no Nash equilibrium. Okay, in this particular game. Now there are also games that have multiple Nash equilibria. And here we are looking at the stag hunt game, where you have two hunters, A and B, and they go together for hunting. If they both go for the stag or the large animal, they have to work together, and in order to get the large animal, if they go separately, they are going for the hare, that they can hunt independently from each other, and they would just get a payoff of 1. So here, think about those two hunters deciding on what to do when they are independently in the woods. And let us see of what the Nash equilibrium in this game is. Now, before we have seen a situation where we have one Nash equilibrium with rock, papers, and scissors. We have seen that there is no Nash equilibrium. Now, let us have a look at a situation where we have two Nash equilibria. So here, this is again a traditional game, stag and hare, where you have two hunters that can get the stag if they are cooperating, or they can get the hare if they are hunting individually for those for the hare. Now here, the question is, what are the equilibria? So suppose that hunter B is going for the stag, then it would be best for hunter A to go for the stag as well. If hunter B goes for the hare, then hunter A should go for the hare as well, because 1 is better than 0, and here 2 is better than 1. Now let us consider the situation where we fix the action of player A. So if player A goes for the stag, then 2 is better than 1. So player B should go, or hunter B should go for the stag as well. And if hunter A goes for the hare, then hunter B should go for the hare as well. So now here, in this situation, we have two Nash equilibria, okay, that either both go to the stag, both go for the stag, or both go for the hare, okay. So here, the Nash equilibria are stag, or hare. Now here, of course, since this we have here a situation where it's cooperation or coordination failure. Now think about this coordination failure in a slightly similar or slightly different context. Suppose that you have an intersection, a four-way stop sign, and you have two cars coming from different direction. Okay, and suppose that this is a stop sign, and they have to, they arrive at the same time at the stop sign. So think about that you have two players, okay, and those two players are driver 1 and driver 2. Okay, and they both have two actions, and that action is either drive or wait. Okay, and now suppose that they are both actually going just straight into the on the opposite side. Okay, now here clearly you have a payoff matrix where if they both drive, then you have an accident. Okay, and if they both wait, then you have an inefficient allocation of resources because they both do not advance. So here again, you would have the situation where you have two Nash equilibria, okay, and that both Nash equilibria are basically that one drives and one waits, or driver 1 drives, driver 2 waits, or driver 1 waits and driver 2 drives. Okay, so here this is similar to the stag hunt game that we have seen before. Now there are also so-called dominant and mixed strategies. A dominant strategy is one that is always the best response regardless of what others do. If all players have dominant strategies, the equilibrium is straightforward. However, in many situations, no dominant strategy exists. In such cases, players may adopt mixed strategies, that is, randomizing across actions to make opponents indifferent and prevent exploitation. Now, let us have a look at dominant strategies as well as mixed strategies given different payoff matrices. Now, a dominant strategy is a strategy where one strategy or one action is always preferred no matter what the other player does. Here in this payoff matrix, we actually have such an example. And here you can see that for player A, action 1 is always better than action 2. Because here you have the payoff of 10 is better than 7, and the payoff of 7 is better than 5, depending on what player B does. The same is true for player B. So player B has a better payoff if they choose 10, no matter what player A does. And the same is true that we have for player B. The action 1 is also better than action 2. So here we have the Nash equilibrium, where we have the 10-10, or both pick action 1. And note that, again, here we have a dominant strategy. Okay, so the Nash equilibrium here is action 1 for player A and action 1 for player B. Now, we have seen before that there are situations where there is no so-called pure strategy Nash equilibrium. The game rock, paper, scissors was one of those examples, and let us have a look here at the second one. Suppose that we have two firms, A and B, that are competing on price, and both firms can either price high or low. Now here, again, as before, we have firm A, and we have in the first position here, and we have firm B that is marked in the second position here. Now, let us have a look of whether there is a pure strategy Nash equilibrium. So suppose that we have firm A that is deciding on whether to price high or low, and assume that the action of firm B is the high price. So in this case, if firm B prices high, then firm A should be pricing high as well. If firm B prices low, then in this case, firm A should be pricing low as well. Now let us switch to firm B. Now consider firm A having or deciding on a strategy of high price. Then firm B should be pricing low, because 70 is better than 40. And if firm A chooses a low price, then firm B should be pricing high, because 30 is better as 20. So here what you can see is that there is no pure strategy Nash equilibrium. Okay, let's write this down. No pure strategy Nash equilibrium. Now, however, we can now see that there is what is called a mixed strategy Nash equilibrium, in the sense that those firms are going to randomize their pricing strategy of high and low. Very similar to the rock, paper, scissors, where the mixed strategy in rock, paper, scissors is to play rock with probability 1/3, paper with probability 1/3, and scissors with probability 1/3. Now here, in order to find a mixed strategy equilibrium, okay, we have to make the firms indifferent, or we have to choose the probabilities such that the firms are indifferent between the various actions. Now let us look at firm A first. Now firm A has to choose a probability row, okay, such that firm B is indifferent between high price and low price. So here we write 40 times row plus 30 times 1 minus row. Okay, so 40, this payoff times rho plus the payoff of 30 times 1 minus rho. That has to be equal to the payoff from 70 and 20. So this would be 70 times rho plus 20 times 1 minus rho. Okay. Now, if you solve this, what you get is 40 times rho plus 30 minus 30 rho equals 70 rho plus 20 minus 20 rho. Now here you can simplify, so you have 10 rho plus 30 has to be equal to 50 rho plus 20. Okay? So now you can see that you have 10. So if you're taking both sides minus 20, so you have 10. You have eliminated the 20 here. And then if you're getting the 10p, the 10 rho, the other side you have 40p, and hence you see that 40 rho, sorry, that rho is equal to 1/4. What that means is that firm A has to play high price in 25% of the cases and has to play low price in 75% of the cases. Now you can do the same for firm B. And here, what you would do is you are now having so you have firm B. And now firm B, what solves 60 lambda plus 10 times 1 minus lambda has to be equal to 30 lambda plus 50 times 1 minus lambda. Okay? Now, if you solve this for lambda, you find that lambda is equal to 4/7. Okay? So what firm B does, or also what firm A does, it is making the other firm indifferent between choosing the action. Okay? So here, if you're thinking about firm B, it is choosing lambda, or 1 minus lambda, such that firm A is indifferent between the 60 and the 10, right? So the 60 times lambda is this part here. 10 times 1 minus lambda is this part here. And then you also have the other side. You have the 30 times lambda is this part here. And you have 50 times lambda, which is this part here. So here, in this case, the mixed strategy Nash equilibrium is for firm A to play high price with probability 1/4, and for firm B to play high price with probability 4/7. Okay, so now here in this case you do have a mixed strategy Nash equilibrium. Now, the last topic that we are going to cover in this video are so-called trigger strategies. In repeated games, players can sustain cooperation through so-called trigger strategies. Each player cooperates as long as everyone else does. Otherwise, punishment is triggered. If anyone cheats, others retaliate by switching to punishment forever, or at least for a fixed period. The threat of future punishment makes cooperation rational if players value future gains enough. The mechanisms explain how firms or countries can maintain cooperation over time. The key idea behind trigger strategies is that the long-term loss from breaking cooperation outweighs any short-term gains. Repeated interaction transforms short-term incentives into enduring relationships. In static games, equilibrium captures immediate stability. In repeated games, strategies can sustain cooperation that would otherwise collapse. That is, in repeated games, an equilibrium can be sustained as a Nash equilibrium that would not be one in a static game. In the cartel context, suppose two firms keep prices high as long as neither undercuts. If one lowers the price, the other retaliates by starting a price war, reducing profits for both. The temptation to cheat brings a one-time gain, but the future losses are large, especially when firms care about long-term profits. The trigger strategy therefore helps maintain collusion until something disrupts the repeated relationship. So now, let us have a look at how this actually works. Now, let us look at what is called a trigger strategy. Here again, consider a game that is very similar to the prisoner's dilemma. If we are looking at the Nash equilibrium here, we have firm 1 and firm 2, and suppose that firm 2 is pricing high. In that case, firm 1 should be pricing low, and if firm 2 prices low, then firm 1 should be pricing low as well. Now, if you are flipping the roles and we are fixing the strategy of firm 1, so firm 1 is going to play the high price, then firm 2 should be pricing low. And if firm 1 prices low, then firm 2 should be pricing low as well. And a pure strategy Nash equilibrium here would be to price low for both firms. Okay, so if we have a single shot game, okay, or a static game, okay, then the Nash equilibrium is that the firms are pricing low and low. But similar to the prisoner's dilemma, we can see that both firms would be better off if they priced high. Now, this is where a so-called trigger strategy comes into play. Now, the term trigger here comes from that there are certain actions in the game that are triggering punishment. Now, suppose that this is a repeated game. So note, a trigger strategy is only possible in a repeated game, in the sense that where you are playing the same game over and over again. Suppose here in this case that those two firms have to decide on pricing on a weekly or on a monthly basis. Okay. Now, then in this case, we can see that the high price of both firms pricing high can be sustained as a Nash equilibrium. Now, basically how this strategy works is consider that the firm 1 is pricing high. Okay. Now, in this case, the firm 1 gets a payoff of 12, and if the firm 1 prices high in the next period, they get a payoff of 12 as well. And suppose that here we have the following trigger strategy. If firm 1, and note that since this is a symmetric game, the same is true also for firm 2. If firm 1 actually deviates in one period and plays low prices in order to get the gain, then the game or the subsequent rounds are going to revert back to the low pricing. So what that means for firm number 1 is that suppose they are playing in the first 2 weeks, they are playing the high pricing, they are getting 12. And note that also firm 2 is pricing high. And then in week 3, they are actually deviating and they're pricing low. Now, in this case, since the firm 2 is pricing high or was under the impression that we are being in a game where we are pricing high, then in that case, firm 1 is going to have a short-term gain of 17. However, punishment is triggered after that, in the sense that now firm 2 is going to price low. Okay? And this for firm 1 would be the resulting payoff. So what you can see is that firm 1, and again equivalently for firm 2, they have to calculate the trade-off between the additional gain from cheating, okay, or from pricing or from deviating from the agreement, so +5. But then in the subsequent periods, they are going to have a severe punishment of -9. And hence it can be shown that pricing strategy of high price can be sustained as a Nash equilibrium in a repeated game. Okay? Note that in any repeated game, the Nash equilibrium from a single shot game, that would be the 8-8, can always be sustained. That is, even if you have a repeated game, the Nash equilibrium from the single shot game is still going to be a Nash equilibrium also in the repeated game.